So you're always looking for that edge, right? That understanding of what's coming next. Well, get ready. Today we're doing a deep dive into tiny, flexible robots.
Hmm.
Seriously, this is tech that could genuinely change how we handle, well, everything from disaster recovery to really delicate medical procedures.
Absolutely. We've been looking at some really fascinating research. It's coming out of Penn State, and the lab manager wrote it up. It shows some incredible steps forward here.
Okay.
Forget those, bulky metal machines you might be picturing. These are soft. They're adaptable. And they could reshape search and rescue medical treatments in ways we're really just starting to figure out.
Right.
So our goal today is basically to break down how these, ingenious things work and, what that might mean down the line.
Okay, so soft robotics. That almost sounds, well, wrong, doesn't it? Robots are metal, gears, rigid things in my head.
Yeah.
What's the core difference here?
Yeah.
And why is being flexible such a, a big deal?
Well, the fundamental difference is really in how they're built.
Yeah.
What they're made of. Traditional robots.
Yeah.
Rigid materials. And that inherently limits how they can move, how they can adapt, especially if the space is uneven or really tight.
Okay.
Soft robots, though, they use flexible materials. They're designed to move, to deform, much more like living things, really.
Ah.
And what's so interesting is that flexibility is the advantage in those really tough spots.
Mhm.
Think about, say, earthquake rubble, a
Yeah.
rigid robot. It could get stuck fast.
Right, easily.
But a soft one, well, potentially it could squeeze through these incredibly tight, sort of awkward gaps and, inside the human body. Same idea. Being able to bend and twist is, well, it's essential if you want to navigate that kind of complex internal landscape.
So for disaster response, the big thing is reaching people you couldn't reach before.
Yeah.
Getting into those spots, that could really boost survival rates. Makes sense.
Exactly.
Now, the article mentions a past problem making these soft robots smart. What was holding that back?
Yeah, that's a really crucial point. Historically, soft robots were mostly, well, you could call them one-way communication systems.
One way? How so?
They needed constant external control, someone guiding every single move, almost like a very fancy remote-controlled toy.
Okay, I see. Limited.
Very. And the Penn State team, led by Huan Yu Larry Cheng, they saw this as a key bottleneck. He actually said, for most applications, soft robotics have been a one-way communication system, meaning they rely on external control. Our goal was to integrate smart sensors so these robots could interact with their surroundings and operate with minimal human intervention.
Right.
So they wanted to give these flexible things some ability to, figure things out on their own.
Okay, so the magic is mixing the softness with the smarts. How did they actually manage that? Because, stuffing normal computer chips into something squishy, that sounds like it wouldn't work.
You put your finger right on the main challenge. Yeah, trying to integrate traditional rigid electronics, that was a huge hurdle. And that's where flexible electronics really came into play. That was the key to enabling these smart features.
Flexible electronics. Okay.
As Cheng put it, we wanted to design a system where soft robotics and flexible electronics work together seamlessly. He points out, traditional electronics are rigid. Our solution was to distribute the electronic components in a way that preserves the robot's flexibility while maintaining robust performance.
Distribute them. So spread out stiff bits so the whole thing can still bend easily.
Exactly. It's about spreading out any stiffness so it doesn't get in the way of the overall movement. Pretty clever, actually.
It is clever. Now, the article also says they move using magnets. That sounds, well, kind of like sci-fi.
It does feel a bit like that, yeah. But the science behind it is pretty elegant. They have tiny bits of what are called hard magnetic materials built into their structure, these little magnets.
Oh, well.
Think of them like how a compass needle reacts to the Earth's magnetic field. So by creating a magnetic field we can steer these robots very precisely.
You just wave a magnet around.
Well, a bit more sophisticated than that. By adjusting the strength and direction of an external magnetic field, the researchers can make the robot bend, twist, even crawl and roll.
Wow.
And the crucial part, no onboard power needed. No batteries, no wires connecting to it.
Huh?
The article even mentions videos showing them crawling and rolling. It actually works.
No batteries dying, no wires getting tangled. That's a massive plus, especially in those, messy, confined spaces we talked about.
Definitely.
But you mentioned even flexible electronics have some stiffness. How did they deal with that? Didn't that cause problems?
It was a significant technical issue, yeah. Cheng noted that Even though we design the electronics to be flexible, their stiffness is still hundreds to thousands of times greater than the soft robotic material.
Okay, so quite a difference.
Right. So their solution, like we touched on, was that strategic distribution, spreading the electronic components out. By doing that, they minimized how stiff any one spot was, so it didn't really compromise the robot's overall ability to bend and move.
Okay, that makes sense now. But what about interference? Electronics can be sensitive, right? Other signals messing things up?
Oh, absolutely. That was another big concern. Unwanted electrical noise from, other devices, wireless signals, that could definitely disrupt things.
Like the control signal or the sensors.
Both, potentially, yeah. Ching mentioned this specifically. He said, magnetic fields are crucial for controlling motion, but they can also disrupt electronic signals. We had to carefully design the electronic layout to minimize these interactions, basically making sure the sensors still worked reliably even with those control magnets active nearby.
Careful layout design.
Exactly, shielding them through clever placement.
So, managing that interference, what new things could the robots do then? What did that unlock?
Well, getting that interference under control was key for a couple of big upgrades. First, it meant more reliable remote control. Using those electromagnetic fields or even just handheld magnets became more practical. Less need for constant, fiddly human input.
Okay, easier to drive.
Right. But maybe more importantly, the fact that the integrated sensors actually worked reliably meant the robots could start to react on their own, autonomously.
Autonomous reactions. Okay, that sounds like a big leap. Can you give me some examples? Like, what would that look like?
Sure. So, search and rescue again. Picture these robots moving through rubble. And maybe detecting a heat signal from someone trapped. Or sensing an obstacle, like a blocked passage, and automatically trying a different route.
Wow, okay. Without someone steering it second by second.
Exactly. And for medical uses, maybe they're designed to react to specific chemical cues, like pH changes in the body, or pressure differences. That could allow for really precise drug delivery right to a target spot. Or maybe collecting a tiny tissue sample for a biopsy accurately.
The medical side sounds potentially revolutionary. The article even talks about a robot pill. I mean, that's quite an image.
It really is. One of the co-authors, Suk-Wan Huang from Korea University, really emphasized this. He said, imagine a small robotic system that could be swallowed like a pill, navigate through the gastrointestinal tract, and detect diseases or deliver drugs precisely where they're needed.
Just swallow it.
That's the idea. So the key insight is moving away from, invasive things like endoscopies towards maybe a future where diagnostics could be, painless, swallowable.
So instead of an endoscopy tube, you might just swallow a tiny robot that sends back pictures or maybe even snips a tiny biopsy. That sounds, way more comfortable.
Definitely.
And delivering drugs right where they're needed, that could cut down on side effects massively, couldn't it?
Precisely. Chang explained it well. With integrated sensors, these robots could measure pH levels, detect abnormalities, and even deliver medication to precise locations inside the body. He talks about, fewer invasive surgeries and more targeted treatments, ultimately leading to improved patient outcomes. That's the goal. And he even looks further ahead, thinking about vascular treatments, suggesting even smaller robots could maybe be injected into blood vessels.
Into blood vessels, wow.
Yeah, to deliver drugs or treat cardiovascular problems much less invasively. I mean, the potential impact on medicine is it's profound.
It's almost hard to really get your head around it. Tiny robots crawling around inside us. It feels like the future is suddenly right here. One last interesting little detail from the article. Apparently, these amazing little things don't even have an official name yet.
That's right. Chang apparently mentioned, sort of jokingly, maybe we should get the public involved in naming them.
Okay.
So yeah, if anyone listening has a great idea for what to call these tiny, potentially life-saving robots, maybe Penn State is listening.
Well, this has been a really, really insightful dive. The potential here with soft robots mixing in these flexible electronics, it genuinely seems like it could transform search and rescue and medical treatments too, offering, more adaptable ways to deal with things, less invasive solutions. It's really exciting stuff.
It really is. And it does leave you with a thought, doesn't it? As this tech keeps evolving and we start seriously thinking about tiny smart robots working in disaster zones or even, inside our own bodies.
Yeah.
What else might come out of this? What unforeseen possibilities, maybe even ethical questions might pop up as this field keeps charging ahead? Definitely something fascinating to keep an eye on.